Hello, this is Coach Ikram, and welcome to this video on acids and bases. In this video, we're going to discuss indicators, neutralization, and titrations. We're going to start by talking about indicators. Indicators are substances that are going to change color in solutions of different pH. They're typically weak acids. They form one color in an acid form and a different color in the base form. So essentially, what's happening here is we've got our acid with the indicator still intact. And when it dissociates, you've got the hydrogen plus comes off of it, and you're left with the indicator ion, which is what forms the color. And indicators are going to help us determine approximate pH because the colors are going to line up with different pHs. There are some limitations to this. The color is subjective. The ranges are kind of narrow, so that makes it difficult with sig figs, and colors can also fade when you're looking at them. But they are still pretty useful, and so here we've got a chart with our indicators. So you notice we've got our indicators on the left. This is the color that they form in acids, the colors that they form in bases or basic solutions, and then that transition color between the two. And then we also have listed here a transitional pH range, which you note lines up with the top end of the acid and the bottom end of the base color. So we're going to use this chart and refer back to it for the next few problems. So I can actually identify the pH of a substance if I test it with different indicators, or at least get pretty close to it and find a fairly specific range. So for example, if I have substance A, and I'm going to use all three of these indicators to try and figure out what its pH is. So I put phenolphthalein in it, and it's colorless. So going back to my chart here, phenolphthalein colorless is less than 8.2. So I know my pH has to be less than 8.2. So what I've done down here is I've got this pink on a number line, which is the best way to do these problems. I've got from 0 until 8.2. So that means my pH must be in that range. Methyl red is yellow. So I'm going to go back. Methyl red is yellow when it's greater than 6.2. So I'm going to go ahead and put this yellow thing right here, and it's greater than 6.2 and goes all the way up. Bromethyl blue is my final one. It's blue in color, and so that means it's got to be a pH of greater than 7.6. And so I've gone ahead and put this blue dash on my number line as greater than 7.6. So you'll note where all three of these lines overlap is where my pH range is. And in this case, if you look at the actual numbers and the values for it, you're going to find that your pH range has to be greater than 7.6, and it has to be less than 8.2. So somewhere between 7.6 and 8.2 is the pH of my particular solution. So it is actually slightly basic. All right, neutralizations. When acids are mixed with bases in equal quantities of hydronium and hydroxide ions, neutralization is going to take place. So we've got our acid, we've got our base, and it's going to react to form a water and a salt. So for example, if I've got 2 HBr plus calcium hydroxide, and that should be a small 2 down here, that's going to yield H2O and my salt, calcium bromide. So when we're talking about neutralizations, we're going to actually we're going to use something called a titration in order to determine the molarity of an unknown solution. So we know the molarity of one of our solutions, and we don't know the molarity of another. And we're going to titrate them to figure that out. So my setup is such. I've got a burette right here, this long tube, and it's containing a base or an acid of a known concentration. I know what this is, and that's going to be my titrant. Then I've got my stopcock, which is a stopper, and I'm going to slowly let that titrant out into my analyte, and that's what's down here. This is my unknown concentration. I don't know what the concentration of this is, and I'm going to add an indicator to this so that as I add my titrant to it, the indicator will change color to let me know when my pH has changed. So the known solution of the titrant is dripped carefully into the unknown solution or the analyte, which contains the indicator. When that new solution is at an equivalent, the analyte concentration can be calculated, and we're going to talk about how to do that using math. In my titration, the equivalence point is going to be the point of neutrality in a titration. So in an acid-base titration, it's when your number of moles of H plus is equal to your number of moles of hydroxide. The end point is the point at which the indicator used in the titration changes colors. Note that that's not necessarily the equivalence point. Ideally, you want it to be as close as possible. You want to use an indicator where the endpoint is as close to the equivalence point that you are trying to achieve. Okay, you want them to be as close as possible. But note that they're not always the same. To solve a titration equation, you're going to have to work from a balanced chemical equation, so that doesn't go away. And you're also going to have to use your mole ratio of acid to base. Again, stoichiometry. You're going to write your known quantities of the reactants, and then you're going to use stoich. And you're always going to start with your volume of your titrant in liters. And this is going to make more sense once we actually do a problem. Start with that volume of titrant in liters. Remember, convert from milliliters to liters first. Don't forget to do that. And then you're going to convert to moles of your titrant using your known molarity. Then you're going to convert from moles of titrant to moles of analyte using the mole-to-mole ratio, stoich. And then you're going to convert to or solve for concentration by dividing by the volume. And all of this is going to make sense when you actually do it. So let's go ahead and solve. All right, so let's go ahead and solve a problem using this knowledge. So I've got 25.0 milliliters of a 1 molar potassium hydroxide solution, and I'm adding that to 46.4 milliliters of an unknown molarity of hydrochloric acid to reach equivalence in a titration. What is the molarity of my acid? So I'm going to start by writing my balanced chemical equation of what's actually happening here. So I've got HCl plus potassium hydroxide yields potassium chloride, my salt, plus my water. And that's all balanced with a 1-to-1 to 1-to-1 ratio. So my instructions, remember from the previous slide, states that I always have to start with the liters of my titrant. Which one is my titrant? Remember, it's the one that you're adding to your unknown, and it's also going to be the one that you know everything about. So in this case, my potassium hydroxide, I know both my concentration and I know my volume. So I'm going to start with it in liters. So I'm going to move that over to the left. So it's 25 mils of 0.025 liters of KOH. And then I'm going to convert to moles using my molarity, because remember, molarity is moles per liter. So if I know the molarity, I know that it's 1.00 moles of KOH for every 1 liter of KOH. Super handy. Go ahead and cross that off. Now that I'm at moles of potassium hydroxide, I can use the mole-to-mole ratio. Never goes away, and I can do stoichiometry. So if I've got 1 mole of KOH, I've got 1 mole of HCl according to my balanced chemical equation. Okay? Now that I'm at moles of HCl, I'm trying to find the molarity of my acid, which remember is also moles per liter. So I have moles, so I'm just going to divide by liters by including it here at the end of my dimensional analysis. So 46.4 milliliters is 0.046 liters of HCl, and that's going to be moles per liter. So I'm all set. So I'm going to go ahead and solve that out, and you should get 0.539 molar of HCl. And there should be 3 significant figures, and there are, and we're all set. Do one more example of this. So we've got a 25 milliliter solution of sulfuric acid, which is a weak acid. And it's of unknown molarity, and it's completely neutralized by 18 milliliters of 1.0 molar sodium hydroxide. So this is going to be my titrant. I know everything about it, and that's what's going to be neutralizing my acid. So I'm going to start with my balanced chemical equation again, very, very important. So I've got H2SO3 plus NaOH, and it's going to yield Na2SO3 plus 2H2O. And I'm going ahead and balancing it as we go. Make sure you don't forget to balance. Very, very important. So 18 mils is going to be 0.018 liters of NaOH. That's my titrant. Use my molarity to convert. So 1.0 moles of NaOH is 1 liter of NaOH. Now that I'm at moles, mole-to-mole ratio, do that stoich. 2 moles of NaOH for every 1 mole of sulfurous acid. Now I can divide by my liters, in order to get my molarity, and that's going to be 0.025 liters of sulfurous acid. And when I solve that out, I got 0.36 molar of sulfurous acid, which also works out with 2 sig figs. And that concludes this video on acids, indicators, neutralization, and titration. Take high quality notes, rewatch as needed, and ask questions in class. Thanks.